In this problem, an individual's eye pupil changes from a diameter of 3.5 millimeters to 1.5 millimeters as the illumination is increased. By what factor does the minimum angle of resolution change? So for this problem, we'll want to take a look at this calculation for the minimum angle of resolution because a human eye pupil is round, so we have to use the expression for a round aperture. So for this, we can use the strategy that we used when we were looking at ideal gas law problems, where we found the things that were changing and the things that were not changing and solved the equation to put the things that were changing on one side and the things that were not changing on the other side. If we use that strategy, we know that the minimum angle of resolution is changing and the diameter of the aperture is changing. Lambda is not changing because we're using the same kind of light, the same color to illuminate the scene. It's just the brightness that is increasing, but not the wavelength. So if we have that expression and we know the things that are changing, we can solve this equation to put all the things that are changing are on one side and all the things that are not on the other. So to do that, we can just multiply both sides by d. So we have theta min times d is equal to 1.22 times lambda. So then since this quantity is not changing, we know that theta min 1, so our initial minimum angle of resolution, times d1 is equal to theta min 2, which is the final angle, times d2. Now what we want to know is how is theta min changing? So let's solve this for theta min 2. So theta min 2, our final angle of resolution, is going to be equal to the initial one, min 1, times d1 divided by d2. So then putting in some numbers, we have theta min 1, and then d1 is our initial diameter, which was 3.5 millimeters, and we want to divide that by the final diameter, which is 1.5 millimeters. So that means that our final angle of resolution is going to be equal to our initial resolution angle times a factor of about 2.33. So that minimum angle will increase by 2.33 times, which means your eyesight is getting a little bit worse as far as being able to distinguish very close together objects because the minimum angle that you can distinguish is getting bigger. So we've seen that as the pupil size increases and decreases, that minimum angle of resolution changes, and it's also going to be dependent upon the wavelength that is being viewed. But for normal vision, we can kind of average over the pupil sizes, the pupil range of sizes, and also we can average over the visible wavelengths and see that on average, for normal vision, the minimum angle of resolution is about 5 times 10 to the minus 4 radians. And if we are looking at a couple of light sources that are separated by some distance s, and we have a distance to those objects of r, that minimum angle is going to be equal to, or the angle between those objects is going to be equal to their separation distance divided by the distance they are away from the viewer. Now, if that angle is bigger than 5 times 10 to the minus 4 radians, then on average, a person will be able to distinguish those two objects. So let's look at an example problem dealing with that. So this example problem asks, how close can 2 grains of salt be to each other and still be resolved by a person with normal visual acuity at a distance of 2.5 meters away? We notice that we're not given a wavelength of light or a pupil diameter, so that must mean we need to use this average value that was mentioned on the previous slide for the minimum visual acuity. So if we do that, and take a look at this problem. We're looking at these salt grains, and we want to know how close can they be to each other. So we have these two salt grains, which of course are little cubes, and these two salt grains are fairly close to each other. They are a distance of s apart, and we know the distance they are to the viewer. So the viewer's eye is going to be 2.5 meters away. So the distance from the eye to the salt grains is 2.5 meters. And we want to know how close can they be to each other. Well, we know that the minimum angle is equal to the separation distance divided by the r, where r is the distance to the object, so this 2.5 meters is our r. And we also know what this minimum angle typically is. So for most lighting conditions and averaging over pupil sizes, we know that this minimum angle of separation is typically about 5 times 10 to the minus 4 radians. So then we can rearrange this expression to solve for S, which is the quantity we know. How close can the two salt crystals be to each other? So S is going to be equal to R times theta min. And R is 2.5 meters. And the average minimum distance, or the average minimum separation angle for normal human vision is 5 times 10 to the minus 4 radians. And so that gives us a separation distance of 1.25 times 10 to the minus 3rd meters. So for an average person with average lighting and viewing conditions, the salt crystals can be no closer together than 1.25 millimeters. If they're closer together than that, they'll kind of blur together and you won't be able to tell that there are two separate salt crystals.